The annulus shown, which by the way, I didn't know this kind of ring plate thing. I didn't know this shape was called an annulus, but the annulus shown has a surface charge density positive. I don't know what that variable is called. It's some Greek letter. The annulus has an inner radius A and an outer radius of B. So this is the top view of the annulus. You know, this stuff is like metal stuff. I don't know, not metal. Yeah, it's probably metal because I guess the charge sits on the top. But the metal stuff, and then there's a hole of radius A, that's the inner radius, and the outer radius is a radius B. So point P exists at a height h above the annulus. So when you look at it from the side, it's like if this was the center, it's a height h above. Find the magnitude of the electric field that exists at point P. You can try this on your own. The textbook that I got this from, if you know university physics, by Young and Friedman, they rate their problems on like 1, 2, 3 dots. So 1 being easy and then 3 dots being hard. This was a 2 dot problem, which compared to the other 2 dot problems in that book, I think this is a 3 dot problem. But it's not too bad, I guess, once you've done some practice with these kind of problems and you know how to do it. So here's the deal with an annulus, right? And we know, so if you think about a ring, like a ring of charge, let's say it's a linear charge density lambda, right? You know, you could pretty easily find like the electric field at a point, I don't know, or at a distance, I don't know, h from the center. That's just a random variable I chose. The annulus is really made up of like a bunch of different rings, right? Ranging from A to B. So what we can do is we can find, well, what is the electric field due to a ring? And then we can integrate whatever that is from A to B, right? Because this is really just a bunch of different rings smushed into one. So, or not smushed, but you know what I mean. Like it's just an essentially infinite amount of thin little rings that we can integrate for. So for a ring like this, remember, there's going to be, if you think about Coulomb's law, it tells us that the electric field is equal to KQ over R squared. This ring will have a radius R or something. Yeah, radius R, sure. And let's use little r. It doesn't matter, but I like little r. So there's going to be a small amount of dq right here. And, you know, that's going to create a very small dE, right? If you were to draw out that distance, this would be square root r squared plus h squared by Pythagorean theorem. So this would be an angle theta, and you know it's a little, this theta is a little different because it's like a 3D. It's like if you visualize this for all points, it would be 3D. So you might be, how do you find the components? Well, for, you know, if you just take the top and bottom one, you see that the x direction component is going to equal the cosine of that, and you're just going to have to kind of trust that for all the other angles, when you do your trig, regardless of the dimensions, it would be cosine theta. I mean, you can just imagine like reorienting it, conceptualizing it like that. The idea is that dEx is equal to cosine theta dE, or dE cosine theta. So to find the electric field, right, dE is equal to K dQ over square root r squared plus h squared, right? That's the distance squared, so that's going to get canceled out, times cosine theta. Let's integrate. So we can integrate. Then you get the total electric field in the x direction, right? Now that I've tacked on the cosine theta, it's going to equal K, and then, so here's the deal, right? So K, this r squared plus h squared, that's a constant, right? That's just a constant you can pull out. And same thing with this cosine theta. This cosine theta is a constant. Now, what is that cosine theta equal to? Well, if you look at your right triangle trig, which hopefully you've done a lot with these kind of problems, it's h over square root r squared plus h squared. So yeah, you can kind of recognize that, hey, that's a constant too. So I can pull that out of the integral and I end up getting times integral dq. I'm just integrating the total charge. And when you integrate the total charge, what do you get? You get whatever the charge is, and we're not even giving the charge. I should have done this in terms of q, but it's fine. KHQ over r squared plus h squared to the 3/2 power. And if you're like, wait, you can just do that, you can in this problem because, this is the only, there's no other variables that will change with respect to q, which is a little weird because, if you think about, when you're integrating, for a rod, right, it's like the height is changing while the q is changing. So some weird calculus stuff that I honestly don't understand yet fully. But just another way to think about it, if you're doing this integral, this is the same as lambda dl, and then your bounds are going to be 0 to 2 pi r, right? Because I'm doing lambda dl, and then it just ends up being 2 pi r. So 2 pi r times lambda just ends up being the total charge. So either way, you get total charge. This is the electric field due to a ring. We got a bunch of rings. So how are we going to deal with that? We got to do it. We got to essentially do this again, but instead of a point charge, we do it for like a ring, right? So now I can say, well, hey, the small amount of electric charge, right? So let's draw this out. I'm going to have a ring. Let's say a ring like so. And I can even draw it here. I'm going to have a ring like so, and I'm going to say it's like a radius r, right? So this ring, it's not just a thin line. It's going to have a little bit of like a thickness to it. Very, 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 very small amount of thickness. Oh, shoot. This is the worst. Just pretend that's like a concentric ring. Just pretend like it's all nice. The thickness of this ring would be dr, like a really, really, really small thickness. So let's do it here too. And why is there at least some amount of thickness? Well, if there's 0 thickness, you would never have gotten a full ring, right? Or a full annulus. So you need a little bit of thickness so that once it accumulates, like when you take that integral with accumulation, it would make the annulus. So this small little thin ring is going to create an electric field, and that the x component of that electric field would be equal to dE, right? So I'm going to say dEx is equal to kh dq over h squared plus r squared to the 3/2 power. I don't have to worry about trig because, hey, I already found the x component when I was doing my ring, so I'm just integrating that entire thing in one direction. So I can just integrate without worrying about trig. Okay, let's integrate. So now we have a problem with the dq stuff, right? I can pull out the kh. So I can pull out the kh, but now I have a problem. Well, okay, my dq, it's like changing as my radius is changing, right? So two variables are changing, the q and the r. I need it to get everything in terms of one variable so I can take this integral. So what I have to realize now is that the surface charge density is equal to the total charge over the total area, but it's also equal to dq over dA. So dq is really equal to whatever that symbol is, dA. So I can say now equal to kh. K, by the way, Coulomb's constant. Hopefully that's not a surprise at this point. Whatever that symbol is, dA over all this fun stuff. The r squared, h squared to 3/2 power. Or r squared plus h squared. So dA, what is dA? It's the area of that ring. So what you can do is because that dr is so small, you can essentially approximate it like a rectangle if you were to like cut it in half and then unravel it, it would be like a triangle where one side is r. Well, not r, but it's the circumference of that ring, right? If you imagine unraveling it, it's going to be 2 pi r times dr, right? So our rectangle is 2 pi r by 2 pi r. And you might be saying, why are we able to make that approximation? Well, to make that approximation, the outer circumference would have to equal the inner circumference, right? So you get 2 pi r, 2 pi r. Otherwise, it wouldn't be a rectangle. Well, dr, when it's so small, that's essentially true. So you can make that approximation. So I get the area, dA, is really just 2 pi r dr. So K equal to kh integral 2 pi r, that symbol, dr, over h squared plus r squared to the 3 has power. Let's pull this over here. We're going to complete this integral. So let's go over here. So e to the x is equal to kh integral. So I'm going to pull out the 2 pi. I don't even know what to call it. I'm just going to call it squib. But I don't know. I can pull out those variables, and then I get left with integral rdr over h squared plus r squared to the 3 halves power. And then my bounds, I'm integrating with respect to radius. My bounds are going to be from a to b. You might be saying, what is the solution of this integral? You would have to do a u sub, right? It's actually not too bad when you do the u sub. Let u equal r squared, du equals 2r dr. You can pull out a 1/2 and then do power, basically product rule, power rule, sorry, and then get the answer. It ends up equaling e to the x, the solution to that integral. So I should really say 2 pi kh. I think that's good notation. 2 pi kh. Is that what the kids do these days? 2 pi kh symbol times, it ends up being -1 over square root h squared plus r squared. And then I'm doing that, my bounds, remember, b to a. So to end off, I essentially get 2 pi kh that over, so -1 over square root h squared plus b squared, right? Fundamental theorem calculus, minus -1 over square root h squared plus a squared. What does that leave me with? That leaves me with, oh my god, 2 pi kh, that symbol. This becomes positive and this becomes negative, so I'm really doing 1 over square root h squared plus a squared minus 1 over square root h squared plus b squared. There you go. That's our answer. To make it a little bit more cleaner, you can say k is really equal to 1 over 4 pi epsilon naught. So I'm just going to do that over here just for fun, times 1 over 4 pi epsilon naught times h over that symbol, then this stuff. So I guess I shouldn't really finish that. I could just say that symbol over 2 epsilon naught times h is times 1 over square root h squared plus b squared, or a squared, minus 1 over square root h squared plus b squared. There you go. That's the whole thing. Just a bit of math at the end, but really hopefully you understand how we're able to connect the ring back to the annulus. And it's kind of a fun problem, honestly. Honestly, it's kind of a fun problem. A couple notes you can pull out. So you can pull out an h and then do some weird, like you could pull out an h squared, and then when you take the square root of that, you get h over h. H would drop out, but then you would have a over h squared. So you can do it. You can go further, but that's the answer. So yeah, hopefully this was somewhat helpful to the 2% of you that would ever need to know this. Thank you for watching.